questions. I love it. See, and it's a direct result of that professor and many others like him that I love it when you guys ask me those questions, because you draw out the best points of this discussion. You draw out the things I'm not thinking of. So thank you for that. All right. 41.5 plus or minus 6%. How far down does it go? 35.5%. Am I doing that math right in my head? 35.5. So that's right about here-ish. And if we add 6, 47.5. Did I do that right? 47.5? Takes it out to about here. That's the actual sample data of the 6% margin of error, which is tied to 95% confidence. 95% confidence. That's the actual sample data tied to its correct margin. So I'm at the University of Sean, replicating the studies that my colleagues have done at LaSalle and NYU and blah, blah, blah. What do? I send the email. What's the first word? Dude. 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 I got the same thing as you guys at Stanford and whatever these two schools were. Chris, ask me that question. I love that look.
No,
it means you're processing something. You good?
Yeah.
You good? Allie, go.
On the margin of error, the 2 times the 0.03.
Yes, ma'am.
That because of 2 standard deviations.
2 standard deviations. That is the Z critical value, and that Z score. You don't remember this from 243. I know you don't, because it's been either 3 months or longer. That Z critical is a number of standard deviations away. 0 would be at average, no standard deviations away. 1 is 1 standard deviation away, 2 is 2 standard deviations away. Very good question. Standard error is essentially a standard deviation for a sample distribution. And then you multiply it to get, you can go out half standard deviations, you can go out quarters, but generally 2 or 1.96 is the bank to use. Fair? Ask me more questions. I love these questions. Please ask more. If you want to, you don't have to either. Please. Tell me your name again, too.
Connor.
Connor, go.
Connor.
Oh, Connor, sorry.
So, how do you pick which level of confidence that you don't pick? How do you calculate that?
Can I ask a question to answer your question? This is a fantastic question. Did everybody hear it? How do you pick 95% confidence? Okay, the easy answer is everybody always does it that way. But that's the you can't go out because I said so answer, and I hate that answer. So I have a question. There are 2 ways to be wrong. Actually, may I hold this question for 4 minutes? I'm going to backtrack. I want to finish the penny spin experiment and backtrack all the way out to answer that, if you don't mind. But let's wrap this up first. Give me 4 minutes, and then we'll backtrack out and help you pick that level of confidence. If that's okay, Connor.
Sounds good.
Because it's a fantastic question. It's one of the cornerstones of this course. 95% is standard, but not always the best. And that goes back to Rory's question. So let's give me 4, and we'll get back. I promise, I promise, I promise. I want to show you some results. First of all, do you see up there why I wrote my colleagues, dude, 50% is not in my interval, correct? Now, if you look at a penny, you might understand why. You might understand why 50% isn't in the interval. But maybe you don't. So what I've done is I've collected this data over years. Over years, I've collected the same experiment that all my students have done using the same pennies. Sometimes I lose pennies, sometimes I have to get more from that same time era, but it's close. Actually, let me turn this off, turn Excel on. We'll come back to this. Results. Oh, wait. Here we go. Here they are. Okay, I added you guys down here. We had 270, and I remembered it being 120, but that was wrong. It was 112, right? Right. I tried to guess. Okay. So if you would, friends, what you're looking at, let's make sure the camera can see this. What you're looking at right here is the results of this experiment from 2006 to the current day. Fall 2006, all the way up to fall 2014. I've kept all the data as much as I can over time. Sometimes I subbed in for Donna's class, so I make their class do it. Like, first thing we're going to do today is spin pennies. They're like, okay, free kippy. I went to Ormatic, did it there at Ormatic, got some data. Notice the sample. These are all the sample sizes I drew. Notice how they vary quite widely. I mean, sometimes 540, 350, 150, very, very small. Donna's class, very, very small that day, 150. Here's the number of heads that I got in each of those classes. So 68 out of 150, 174 out of 400. Remember the question I asked you guys a little while ago? I said, do you think if I repeat this experiment again, I'll get the same percentage of heads? And you guys said, no, you probably won't. Well, here's what I have been getting. Look at that. Now look at that. That one jumps away. That's significantly different, yeah? And then you get these, and so I see this variation, which is sampling error. It's sampling error. That's going to happen naturally in the spinning of pennies. They're not always going to come up. It's like saying that flipping coins 50-50 goes heads, tails, heads, tails, heads, tails. No, it doesn't. No, it doesn't come at you that neatly. It clumps. And you're seeing the clumps in small segments and small packets here. So then I said, because we're human beings, let's actually draw it out graphically. Let me see if I can pull this down so it lines up with the actual data a little better. Whoa, that's too big. That's close. So here's the interval we just calculated with you guys. This is the 50% line right here. That's the 50% line. Notice how your guys does not touch the 50% line, correct? But notice how the class in the spring did. And the class in winter did. And as a matter of fact, the past couple classes did. But then if you go back historically through time, notice quite a few did not. Quite a few did not, and quite a few did. Now, please, Ben, go.
Is it the nature of a large overtime projection that it's going to have a pretty
No,
squiggle?
that squiggle is fun, and I'm gonna come back to that. That's okay. Ben's saying there's like a pattern that it squiggles, and I can't explain that. I can't explain the squiggle pattern because this is a pretty uncontrolled experiment. I mean, I say spin pennies, assuming you guys know how to spin pennies. So there's all kinds of other non-sampling error that's in here, but I can't explain the squiggle. It's pretty rad though.
Basics of physics over 20
If it is, I don't understand. The equinox versus the non-equinox, I don't know the answer to that one, unfortunately. Do you notice how some of the intervals are wider than others? Why?
Because you have larger samples and smaller samples?
Larger and smaller samples govern how wide the interval is. Now, mathematically, see if that makes sense to you guys. Remember this calculation right here? Remember this calculation right here? What's in the denominator? The sample size. Remember what Chris said before? The larger a sample, the smaller the margin should be. Well, the bigger the denominator of a fraction gets, shouldn't the overall fraction get smaller? Boom. That's the mathematics behind the logic and the intuition. Very nice, very nice. Connor, I forgot your question, I promise. Now, the widest intervals are the ones that correspond to the smallest samples. And conversely, the smallest intervals are the ones that correspond to the largest samples. And I couldn't resist. I couldn't resist. Up top up here, I put all of it together into one uber sample. That's the confidence interval for all of the results over time. It covers an average of 44%. It's still a p-hat. It's a historic p-hat, though. I couldn't make the hat symbol in Excel, sorry. So imagine a hat with that. Historically, I've seen 44% heads and 56% tails. So now what's the next question I ask? Why do I see a lower? That becomes significant. That's what we call a statistically significant difference from 50%, because the margin of error on that is way less than 3%. It's no longer even close to touching 50%. So my question is why? And this is outside the scope of 244, but go!
The head, the picture on the head sticks out and the picture on the tail is indented.
That is my theory. My theory is there is more metal on the head side. And when you start spinning it, inertia, object in motion tends to stay in motion. More mass equals wants to spin more, which means it's not going to give up spinning. It's going to spin itself right down. Tails gives up. You see tails more because it gives up more easily. That's my theory. It seems to it hangs with science okay, I think. That's my theory of why that happens. Rory.
Don't they always spin in though? Like when you spin it in, doesn't it always fall in?
That was a theory brought up by somebody last time. Sean, he's not here today. Sean, if you're watching. He had a theory that depending on how you lay the coin down and spin, that governs it. I had never controlled for that.
Yeah.
I've never controlled for that, but a couple Google searches show that other people have the same theory. So I'm guessing it either hasn't been tested or it's been shown to be not as inconclusive, so to speak. I have no good answer. I have no perfect answer for you for that, though. The great question, though. And that's it. See, this is what's cool about like this kind of mathematics is it takes you to the door, shows you the result, and then it's up to you to discover what happened or what didn't happen. And that's where your individual expertise that you're studying in your different programs take over. Those of you guys in natural resources or science, that's where you go. You figure more heads, more metal on the head side, right? Oh, that rehabilitation seems to show significant differences. Why? Why? Oh, because you actually targeted the teres directly as opposed to tangentially, or something like that. There's all that. You escape me at that point. That's when you guys run with it. You ever seen not The Fugitive, Clear and Present Danger, Harrison Ford? when he gives the kid the computer, a little tiny computer task. And Harrison Ford's a smart dude in that film, but he takes it to a point, he shows this kid the tool, and this kid this tool, and this kid goes, and then I can do this, and then I can do this, and Harrison just turns him around slowly, the computer, taps him on the shoulder, and walks away. Because that's what I'm doing with you guys. Here's a tool, run with it. See what you can do with it. Yes, fair? So what do we got today so far? We've learned about confidence. Now, what does the confidence mean? Let's finish with this before we get into Connor's question. When I say 95% confidence, what does that mean to you? Interpret that for me. So, let me give you a less loaded question. We just calculated. Oh, let me do this actually. We just calculated over here. The colors on these things are awesome. Look at that. That green interval right there.